Welcome to G Fun Facts Online. Let's start with a simple question. What if I told you that scientists have created ice that is solid at room temperature? Not the reusable plastic cubes in your freezer, but real ice made from water that doesn't melt at 77 degrees Fahrenheit. It sounds like science fiction, but it's now science fact. The catch? This strange new ice, called Ice XXI, only exists under immense, crushing pressure. Its discovery forces us to rethink everything we thought we knew about water, opens new windows into distant alien worlds, and hints at a future where we can create impossible new materials on demand. Today, we're journeying into the unseen world of water to uncover the mystery of Ice XXI. Before we can understand this impossible ice, we first need to reconsider the ice we think we know. The stuff that floats in your drink is called Ice IH. The H stands for hexagonal, which describes the repeating crystal structure of the water molecules. In liquid water, molecules are jumbled and slide past each other. But as water freezes into Ice IH, the molecules arrange themselves into a specific, open, six-sided lattice. This open structure is actually less dense than the liquid it came from. This is a profound anomaly. Almost every other substance becomes denser when it freezes. Water's strange behavior is the reason icebergs float, and it's what allows aquatic life to survive winters under a protective frozen surface. But this familiar life-giving ice is a product of our planet's gentle atmospheric pressure. What happens when you subject water to pressures thousands or even millions of times greater? The rules change completely. The universe pushes the water molecules to rearrange into more compact, denser forms, giving birth to an entire zoo of exotic, high-pressure ices. Our exploration of this zoo began in the early 20th century with American physicist Percy Bridgman. He invented equipment that could squeeze materials with incredible force. In 1912, he discovered 5 new types of ice, which he labeled Ice II, Ice III, Ice V, and Ice VI. He showed that by squeezing water, you could force it to freeze at temperatures well above its normal freezing point. He even created hot ice, stable at temperatures higher than boiling water, as long as the pressure was maintained at tens of thousands of atmospheres. Bridgman's work, which earned him a Nobel Prize, opened the floodgates. As technology improved, scientists discovered more and more ice polymorphs. There's Ice VII, which has a simple cubic structure and is found at pressures above 20,000 atmospheres. And then there's one of the most bizarre forms of matter imaginable, superionic ice, or Ice XVIII. Confirmed in 2018, this stuff forms at over 100 gigapascals of pressure and thousands of degrees Celsius. Here, the water molecules break apart. The oxygen atoms form a solid crystal lattice, but the hydrogen ions flow like a liquid through that solid framework. It's a state of matter that is both solid and liquid at the same time, and it's believed to make up the mantles of ice giants like Uranus and Neptune, possibly explaining their strange magnetic fields. By the 21st century, we knew of 20 different phases of ice. Into this already crowded landscape, a new, completely unexpected member was just born, Ice XXI. The discovery of Ice XXI was a global effort, led by researchers in Korea and Germany, using some of the most powerful scientific instruments on Earth. The experiment wasn't just about applying immense pressure, it was about applying it with incredible speed. The team used a device called a dynamic diamond anvil cell, or DDAC. Imagine taking 2 flawless, gem-quality diamonds and polishing their tips to a perfectly flat point. You place a tiny droplet of water in a little chamber between these tips, and then squeeze them together. Because diamonds are the hardest known material, this simple setup can generate pressures similar to those at the center of the Earth. The dynamic part of this device uses powerful actuators to drive the diamonds together at blinding speeds. Here's how the experiment worked. First, they took a minuscule water sample at room temperature. Then, they ramped up the pressure with astonishing speed, reaching 2 gigapascals. That's about 20,000 times the air pressure around you right now, in just a few milliseconds. This created a bizarre state called super compressed water, where the water remained liquid at a pressure where it should have frozen. Then, the pressure was released more slowly. This entire crush-and-release cycle was repeated over 1,000 times. To see what was happening during these fleeting moments, the scientists needed an ultra-high-speed camera for molecules. They used the European X-ray free electron laser, the world's most powerful X-ray laser. By firing incredibly short, brilliant pulses of X-rays in sync with the pressure cycles, they could capture snapshots of the water's molecular structure every millionth of a second. It was like creating a stop-motion movie of water freezing under pressure. The results were stunning. The water didn't just smoothly freeze into the expected stable form of ice for that pressure, which is Ice XXI. Instead, the researchers saw multiple, complex freezing pathways. And along one of these pathways, for just a fleeting moment, a completely new, previously unseen phase of ice appeared. They named it Ice XXI. Further analysis revealed its structure, a complex body-centered tetragonal crystal, significantly denser than ordinary ice. So how is this possible? How can you make a type of ice that should exist? The answer lies in the difference between thermodynamics and kinetics. Thermodynamics tells us what the most stable, lowest energy state of a system is. For water at room temperature and 2 gigapascals of pressure, that stable state is ice fix. But thermodynamics doesn't tell us how fast the system will get there. That's the job of kinetics. The key to creating Ice XXI is the speed of compression. When you squeeze water slowly, the molecules have time to jiggle around, find their partners, and neatly arrange themselves into the stable Ice XXI crystal. But by slamming the pressure on in milliseconds, the researchers don't give the system time to find that perfect arrangement. The molecules are jammed together, trapped in a highly stressed, super compressed liquid state. From this state, the system is desperate to solidify, but it's been pushed so far from equilibrium so quickly that it gets lost on its way to the most stable structure. Imagine a ball rolling down a bumpy hill. The very bottom of the hill is the most stable state, like Ice XXI. If the ball rolls slowly, it will find its way to the bottom. But if you give it a hard, fast push, it might get bounced into a small pothole partway down the hill. In that pothole, it's temporarily stable. That pothole is Ice XXI. This phenomenon is called kinetic trapping. The discovery of Ice XXI proves that the journey from liquid water to high-pressure ice isn't a single, simple step. It's a complex landscape with multiple roads, and by controlling the speed of the journey, you can trap water in these hidden, temporary states. Now, let's be clear about the headline: ice that doesn't melt. Ice XXI is indeed solid at room temperature, but only because it's being held together by that immense 20,000 atmosphere pressure. If you could somehow take a cube of Ice XXI out of the diamond anvil cell, it wouldn't sit on your desk. The instant the pressure was released, it would explosively revert to liquid water. This is completely different from the non-melting ice cubes or whiskey stones you can buy. Those are usually cubes of steel or granite that you freeze. They cool your drink simply by absorbing heat. They don't melt because they're already stable solids at room temperature. They are simply transferring thermal energy. Ice XXI, on the other hand, is a true phase of water, held in a solid state by physics, not by low temperature. So if we can't make permanent room temperature ice cubes, why does this discovery matter? The implications are huge, starting with planetary science. Moons in our outer solar system, like Jupiter's Europa and Saturn's Ganymede and Titan, are thought to have vast liquid water oceans buried beneath thick shells of ice. The pressures inside these shells are enormous, creating perfect conditions for high-pressure ices like Ice III, Ice V, and Ice XXI. Our current models of these moons assume that water always forms its most stable ice phase at any given depth, but the discovery of Ice XXI challenges that. It suggests that rapid pressure changes, perhaps caused by a meteorite impact or an underwater volcanic eruption, could trap water in metastable ice forms. These temporary ices would have different densities and different thermal properties than their stable counterparts. This could completely change our models. Pockets of less dense or more dense metastable ice could affect buoyancy and convection within the ice shell, influencing the geology we see on the surface. It could alter how heat escapes from the moon's core, affecting the temperature of the ocean and the overall habitability of that alien world. The possibility of these new kinetic pathways gives us a richer, more complex picture of how these icy worlds might work. Beyond understanding alien worlds, the ability to create and control novel materials like Ice XXI opens up speculative but exciting possibilities here on Earth. Metastable materials are all around us. Diamond, for instance, is a metastable phase of carbon. Over millions of years, it would prefer to turn into graphite. We prize materials like diamond precisely for their unique metastable properties. The technique used to create Ice XXI, using rapid compression and kinetic trapping, could be applied to other substances to synthesize new materials. Imagine creating novel materials for energy storage, where energy is stored in the structure of a metastable phase. In pharmaceuticals, the crystal structure of a drug can dramatically affect how well it works. This technique could help create more effective, but normally unstable, drug forms. In electronics, high-pressure synthesis is a key tool in the search for new superconductors. The ability to trap materials in novel crystal structures could accelerate the discovery of materials with exotic electronic or magnetic properties. The direct use of Ice XXI is unlikely, but the knowledge we've gained, the mastery over the kinetics of phase transitions, is a powerful new tool. It's a step towards a new paradigm of